Hi, this is Mrs. Schoaf. Today our objective is to be able to simplify radicals involving rationalizing the denominator. This is Chapter 9, Section 1. When we simplify radicals, the denominator cannot contain a radical expression and must be simplified. If there is a radical expression in the denominator, it must be rationalized. So we call it rationalizing when we get rid of the radical sign in the denominator. For example, this first problem is not simplified because we have the radical sign in the denominator around the 300. The second one has a radical sign in the denominator. The bottom one has a radical sign in the denominator here around 85. So our goal today is to simplify by getting rid of the radical sign in the denominator, and it's called rationalizing the denominator. If I look at number 1, I'm noticing that 49 and 4 are perfect square numbers. So this one's actually pretty easy because you can take the square root of 49 to get 7, the square root of 4 to get 2, and then we do not have a radical sign in the denominator. So you could say it's 7 over 2 or 3.5. Looking at number 2, 3 is not a perfect square number, 10 is not a perfect square number, and this is not simplified because I have a radical in the denominator. So I need to multiply by a fraction that's the same as one whole, such as 7 over 7, 8 over 8, 9 over 9. But I'm trying to get a perfect square number in the denominator so that I could take the square root of that number and not have a radical sign anymore. Like on number 1 when I took the square root of 4 and I got 2. So I want to think about my perfect square numbers, 1, 4, 9, 16, 25, 36, and so on. I'm trying to multiply 3 by some number so I get one of these perfect square numbers. Well, I notice 3 goes into 9. I could take the square root of 3 times the square root of 3, and I would get the square root of 9. 9 is a perfect square number because the square root of 9 is 3. Now I no longer have a radical in the denominator. Well, if I multiply the denominator by radical 3, I've got to multiply the numerator by radical 3 because this would be the same as multiplying by 1. So when I take square root of 10 times square root of 3, I get square root of 30. So I have the square root of 30 over 3. Sometimes students want to go ahead and divide this and make it the square root of 10, but you cannot divide the 30 into 3 because the 30 is under a radical sign and the 3 is not. So you cannot divide them unless they're both under the radical. You also want to check to make sure there are no perfect square numbers that go into 30 to make sure it's simplified all the way. 4 won't go into 30, 9 won't go into 30, 16, 25. So we're okay. No perfect square numbers go into 30, so my final answer would be square root of 30 over 3. So our goal is to get rid of the radical sign in the denominator in order to rationalize it. So if you look at number 3, I've got the square root of 6 in the denominator. 6 is not a perfect square number. So I start thinking about, well, what can I multiply by 6 to get one of these square root, or perfect square numbers up here? 6 goes into 36. So what I'm going to do is multiply by the square root of 6. Because square root of 6 times square root of 6 gives me square root of 36. And then I know square root of 36 is just a 6. So I get a whole number instead of a radical sign left in the denominator. Well, if I multiply the denominator by radical 6, I have to multiply the numerator by radical 6. So I'm multiplying this fraction by the square root of 6 over square root of 6, which is the same as 1. That's how I'm not changing the value of this fraction, I'm just multiplying by 1. So square root of 2 times square root of 6 is square root of 12. Remember, you cannot divide these because the 12 is under the radical and the 6 is not. So some people want to look at that and say, oh, that's the square root of 2. No, you can't divide because 12 is under the radical and 6 is not. But there is a perfect square number 4 that goes into 12, so we can simplify further. We're going to work this down into the square root of 4 times the square root of 3 over 6. So then the square root of 4 is 2. I have 2 radical 3 over 6. I can simplify further because 2 goes into 2 once and 2 goes into 6 3 times. The reason I can simplify the 2 and the 6 is because they're not under radicals. I could not cancel this 3 and the 6 because the 3 was under a radical and the 6 is not. But I can simplify this to 1 radical 3. If you have 1 radical 3, that's the same as radical 3 over 3. Remember, you can't divide this and say it's the square root of 1 because 3 is under a radical and this 3 in the denominator is not. So your answer is just the square root of 3 over 3. Okay, number 4, I've got a radical in the denominator. I got to get rid of that by rationalizing the denominator. I'm going to go ahead and multiply by the square root of 6. When I do this, I'll get the square root of 36 in the denominator. The square root of 36 is 6. So now the radical is gone in the denominator. In the numerator, I cannot take the 4 times the square root of 6 because 4 is not under a radical and 6 is. So really what I have is 4 radical 6. So I have 4 radical 6 over 6. Could I simplify this further? Yes, I could. I could cancel the 4 and the 6 because 2 goes into both of those. I could say 2 goes into 4 twice. 2 goes into 6 3 times. So I'm going to cross off the 6 and make it a 3. I cannot cancel the square root of 6 with this 3 because the 6 is under a radical and the 3 is not. So my answer would be 2 radical 6 over 3. My final answer is 2 radical 6 over 3. Let me make that a little neater. Okay, number 5, I have the square root of 3/10. The square root of 3/10 is really the same as the square root of 3 over the square root of 10. But 10 is not a perfect square number. I could get a perfect square number in the denominator by multiplying by radical 10 over radical 10. Because then I'd have the square root of 10 times the square root of 10, which would be the square root of 100. The square root of 100 is just a 10. So see how I get rid of the radical in the denominator? I get a whole number of 10. When I take the square root of 3 times the square root of 10, I do get the square root of 30. I can multiply them because they're both under radicals. The question is the square root of 30 over 10 simplified? Could I divide 30 and 10? No, I cannot, because 30 is under a radical and 10 is not. Are there any perfect squares that go into 30? 4, no. 9, no. 16, no. 25, no. 36, no. So this would be my final answer. Okay, number 6 has 1 over square root of a. Well, I cannot leave the radical sign in the denominator. So what I could do is multiply the square by the square root of a over the square root of a. Because then I'll get the square root of a squared, and the square root of a squared is just a. Then I could take 1 times the square root of a, which would just be a square root of a. I would end up with square root of a over a. Could I simplify it? No, I cannot. I can't cancel my a's or divide my a's because this a is under a radical and this one's not. So this would be my final answer. I'm having a hard time drawing the box today. There we go. All right, number 7 is not simplified because there's a radical in the denominator. So I need to get rid of this radical square root of 18m. Now I could multiply by the square root of 18m, or I could multiply by the square root of 2m. Because if you take 18 times 2, you get 36, and 36 is a perfect square number. It wouldn't be wrong to multiply by the square root of 18m. It's just a larger number. You still get a perfect square number. But I'm going to go ahead and do it this way so that I get the square root of 36m to the second. M times m is n to the second. And then when I take the square root of 36, I get 6. The square root of m squared, I get m. So now I no longer have a radical in the denominator. Well, if I multiply the denominator by radical 2m, I need to multiply the numerator by radical 2m. So I can multiply the 5 and the 2m because they're both under radicals to get the square root of 10m. So I've got the square root of 10m over 6m. Could I simplify? Well, there are no perfect square numbers that go into 10, 4 and 9 and 16. They won't work. I can't cancel these m's because this m is under a radical and this one's not. And I can't divide by 2 with the 10 and the 6 because the 10 is under a radical and the 6 is not. So this is my final answer. Okay, looking at number 8. I have the square root of 2n in the denominator. So I need to rationalize the denominator by multiplying by the square root of 2n. Because then in the denominator, I'll get the square root of 2 times 2, 4, n times n squared. Well, I could take the square root of 4n squared and just get a 2n. Now I no longer have a radical. In the numerator, when I take the square root of 6 times the square root of 2n, I get the square root of 12n. So let's think about this. Could I simplify any further? I can't divide 12 and 2 because 12 is under a radical and 2 is not. I can't cancel my n's because this one's under a radical and this one's not. Is there a perfect square number that goes into 12? Yes, there is, 4. So I could break this down into the square root of 4 times the square root of 3n, all over 2n. Well, the square root of 4 is 2, so I'd have 2 radical 3n over 2n. Could I simplify any further? Yes, I could. I could cancel these 2's. 2 goes into 2 once, 2 goes into 2 once because they're not under radicals. And then I would have the square root of 3n over n. Could I simplify any further? No, I cannot, because this n is under a radical and this n's not. So my answer is just radical 3n over n. Okay, on number 9, I have the square root of 180 over the square root of 3. There are a couple ways you could do this problem. You could just multiply by the square root of 3 over the square root of 3, so that you get the square root of 9 in the denominator, and then the square root of 9 is 3. You're going to get a large number here. You're going to get 540, and you're going to have to see if you can simplify that. So is there a perfect square number that goes into 540? Well, 9 does. 9 times 60. So you could say this is the square root of 9 times the square root of 60. Square root of 9 is 3. Could I simplify radical 60? Well, 4 goes into 60, so you could say this is the same as the square root of 4 times the square root of 15 over 3. Square root of 4 is 2, although I'm noticing 3 and 3 could be canceled because they're not under radicals. So I could say 3 goes into 3 once, 3 goes into 3 once. The square root of 4 is 2, and then I have radical 15. Do you see another way I could do number 9? Actually, what you could do is you could divide 180 and 3 because they're both under radicals. So you could take 180 divided by 3, and that would just be the square root of 60. And then you can say, what's a perfect square number that goes into 60? That would be 4. So I would have radical 4 times radical 15. The square root of 4 is 2. So my final answer is still 2 radical 15. Okay, looking at number 10, we have variables. I'm noticing I have a radical in the denominator, so I'm going to have to multiply by something to get rid of that radical. I need to make this a perfect square. Remember, we can take square roots of variables to even powers. You could just put y here to get y to the 4th, because the square root of y to the 4th is y to the 2nd. So here's one way you could do it. If you did it that way, well, I'm noticing x to the 2nd is a perfect square. The square root of x to the 2nd is x. So I would have an x times radical y. This would be an x radical y. So I just said the square root of x squared, that is x. When I multiply that by square root of y, I get x square root of y. So I have x square root of y over y to the second. Could I cancel a y? No, I can't, because this y is under a radical and this one, the y to the second is not under a radical. Now, there was another way you could do this problem. Some people might do it this way. They might look at it and say, well, I'm just going to multiply by radical y to the third, because that would give me radical y to the sixth, and the square root of y to the sixth is y to the third. Then what you'll have is x, because the square root of x squared is x, radical y to the third. So if I have x radical y to the third, could I cancel y's? Could I cancel the y to the third and the y to the third? No, I can't, because this one's under a radical and this one's not. But you could say this y to the third is the same as the square root of y squared times y. Because you can take the square root of y squared. Square root of y squared is y. So I will have an x y radical y over y to the third. So what I did is I took the square root of y to the second and got this y. This x comes from here, and I still have a radical y. Do you think that's simplified all the way? No, it's not, because I can cancel this y with one of these y's, and that'll leave me with y to the second. So my answer would be x radical y over y to the second. So wait a minute, can I cancel this y with one of these y's? No, I can't, because this y is under a radical and this one's not. But notice I got the same answer. Here's the same answer, x radical y over y to the second. It is a little easier just to multiply by radical y, and then just get radical y to the fourth, which will give you y to the second. So to review our objective, we were trying to simplify our radicals by rationalizing the denominator. Rationalizing the denominator means getting rid of the radical in the denominator. Today your assignment is page 486, numbers 45 to 52 all. You're going to go to the Big Ideas online textbook and enter your answers there.